So let's do this example. We'll first start with surface integrals over scalar fields. So here we want to evaluate this surface integral where s is the part of the paraboloid x equals y squared plus z squared, given that x is between 0 and 1. So if you want to think about what this looks like, well, a paraboloid, you can see that the paraboloid itself is oriented over in the x direction. So you're going to start at the origin and then go all the way to 1. Okay, so you got all of this guy. So this is going to be your paraboloid. If you want a physical interpretation of what exactly we are doing, imagine that this z squared is your density. So how dense this paraboloid is at every point. And what you really want to do is you're multiplying it by the surface area, which is this guy. This is going to be the surface area. And when you're multiplying this guy out and adding every single little patch, what's happening is that you're calculating the mass. So essentially, this guy is just going to give you the mass of this particular paraboloid. It's just kind of to give you a little bit of a glimpse of what exactly this guy is doing. So let's go ahead and set it up. First things first, we got to parametrize this paraboloid. Luckily, it's not a bad one. It's a pretty simple one. So if we just let y be y and z be z, this looks like a g. So if my y and z are, if I treat those as my two parameters, then I can just let x be y squared plus z squared. And you can see that this x is just going to be my g of yz. Okay. So a way that you can try to write it into parametric equations, and you can start doing that because it'll be a little helpful when you work with it in vector fields, would be r of yz. So those r is my vector function, and it has two parameters, y and z. You can write it as the x parametric equation, which is y squared plus z squared. Then for y is just y, and for z is just z. So if you want to write it like that, you can also do so. Now we'll use the formula, which we know is going to be the double integral over the surface S, f of x comma y comma z, ds. And we're going to use the formula oriented over in the x direction. So over d, f of g of y comma z, y, z. And then it's going to be the square root of g, partial derivative of g with respect to y squared, and then of z squared plus 1. So just plugging everything in there. So if we kind of look at this, we first gotta look at our surface integral. So you can see that in the inside we have z squared. So that's gonna go in here. So it's gonna be the double integral over d. Now z squared in that case, and if we look at our parametric equation, we don't really got to do anything. The only thing that we really want is y's and z's. That's based on my parametric equation. I only want y's and z's. So this z squared is pretty good. If I would have had an x in there, I would have to plug in y squared plus z squared. Okay, and now we have the square root of the derivatives. So let's take the partial derivative with respect to y. So that guy corresponds with this guy. Because remember, that was g of yz. So the partial derivative in that case is 2y. Then we're going to square that. Then the other one's 2z. We're going to square that, and then plus 1 dA. All right, so this is going to be the double integral over the region D of z squared. And in the inside, we're going to have 4y squared plus 4z squared plus 1 dA. So what we have to do now is we have to figure out what my region is. So if you look here, you see that you're going from x equals 0 all the way to x equals 1. So if you think about what's happening, what are those regions? At x equals 0, when I plug it into the paraboloid, I'm going to get 0 equals y squared plus z squared, which is pretty much a point, which we kind of already knew. Now what's going to be the region in this case? Well, we can see that it's going to be a circle. A circle, when x equals 1, is going to be a circle of radius 1. So you can see that it's going from a circle of radius 0, you can think about it that way, to a circle of radius 1. So it would be best to convert this to polar coordinates. So we're going to let my x, well, there's no x. So since it's oriented in the x direction, we're going to let our z now take the control of whatever x was, which was r cosine theta. And y in this case is going to be r sine theta. And obviously, y squared plus z squared is going to be equal to r squared. So let's go ahead and substitute everything in there. So we can see that my theta value is going to be from 0 to 2 pi because it's a whole circle. Then my circles are going to go from radius 0 to radius 1. Then we have z. Z in this case is equal to what would z be? Z is r cosine theta, so that will be r squared cosine squared theta. And then in the inside, notice that we can factor out of 4. Y squared plus z squared will just give me r squared plus 1. And then we got to figure out what dA is. That's just going to be in polar r dr d theta. So let's clean this up. 0 to 2 pi, 0 to 1. This was going to give me this r, and this r will give me r cubed cosine squared theta, the square root of 4r squared plus 1 dr d theta. Now at this point, we kind of have an issue. And you'll see what the issue is in a second. But let's first split it up because you can see that I can put cosines and r, so I can multiply using a double integral property. I can just put my theta integral over here, cosine squared theta. And then I can just do my r integral, 0 to 1, r cubed square root of 4r squared plus 1 dr d theta. Okay, so before I start working with the cosine, with the r, let's work with the cosine first. So I'm going to leave this one, which is going to be a little more complex there for a second. But we can do the cosine. The cosine's a little easy. So let's convert this to using the reduction formula. So you're going to have 1/2, 1 plus cosine 2 theta, d theta. Then the integral from 0 to 1, r cubed, square root of 4r squared plus 1 dr. So I can pull out the 1/2, and then you can take the integral of this inside part, and that inside part, let me just color it in green, I'm going to have theta plus 1/2 the sine of 2 theta. And this is going to be from 0 to 2 pi. And then the rest of it, which in this case will just give me the integral from 0 to 1, r cubed square root of 4r squared plus 1 dr. So using the fundamental theorem of calculus, I can see that that guy is just going to give me 1/2. In the inside, the only thing that's going to take into account is that 2 pi to the theta, because everything else is going to go to 0. So you're just going to get 2 pi there. And then we're just going to be left with the integral from 0 to 1, r cubed square root of 4r squared plus 1 dr. So we finally arrive at this point. So we got pi integral from 0 to 1 r cubed square root of 4r squared plus 1 dr. So here's where we have a couple options. One of the things that you can do is you can use trig sub. So trig sub is kind of annoying. I would not want to use that one. Instead, what I'm going to do is I'm going to use a fancy u substitution. So I'm going to let u be equal to 4r squared plus 1. So that means that my du in this case is going to be equal to 8r dr. Can move the 1/8 over, du equals r dr. Now, if you see it, we don't have an r cubed in here. So this is what I'm going to do. So if I let u be the outside function, okay, I'm sorry, the inside function, then what am I going to do with that r cubed? Well, I'm going to do something really fancy. So I'm going to use a fancy integration. So I'm going to let pi be that from 0 to 1. I'm going to multiply, or I'm going to break up that r cubed to r times r squared, square root of 4r squared plus 1 dr. Okay? And what happens here is that now I can just take everything in there, or substitute everything in there. So you can see that rdr, so see how we have this rdr right here. That guy is just equal to this 1/8 du. So I'm going to substitute that in, 1/8 du. Now we have that square root thing. So we have the square root right there. The inside of the square root, I'm going to substitute that by whatever I let u equal to, which in that case is going to be that u. Now there's only one thing that I'm kind of concerned about, and that's that r squared. What am I going to do with that r squared? This guy. Well, if you notice, this u has an r squared in there. So why don't I solve for r squared and see what I get? So I subtract the 1 over, I get u minus 1 equals 4r squared. Divide by 4, r squared equals u minus 1 over 4. So that means I can also substitute by manipulation over here, substitute the r squared with u minus 1 over 4, which is something that you might have seen in Calc 1 or even in Calc 1, in Calc 2, even in Calc 1, maybe. But Calc 2, usually you use this little fancy u substitution. So you're going to have a u minus 1 over 4. And now here, I can do my limits of integration. So you can do multiple things. You can switch them over to u. I'll switch them over to u in a second. Or you can just leave them as r. But if you leave them as r, you're going to have to remember that these are limits of integration for r. Okay. Okay, so now I can move stuff over. So I'm going to have the 1/8 and the 4 I can take out. So it will be pi over 32. The integral from 0 to 1. Okay, let's go ahead and so you can continue writing it like that, or you can just do a substitution. Since I know that u equals 4r squared plus 1, I'm going to figure out what the limits of integration are in terms of u. So plugging in 0, I get u equals 1. Plugging in 1, I'm going to get, what is that? 1 squared plus 5. So u equals 5. So again, you don't need to do this. You can continue writing r equals 0, r equals 1 until you finish it, or you can just substitute it now. So I'm going to have u minus 1 square root of u du. So I'm going to have the pi over 32 integral from 1 to 5. Square root of u is u to the 1/2. So that's going to give me u to the 3/2 when I distribute it, minus u to the 1/2 du. So that's distributing in the square roots. And now all we got to do is just take the antiderivative of this guy. So taking the antiderivative, I'm going to get pi over 32. Okay, I'm going to take the antiderivative of this guy. You're going to get 2 over 5 u to the 5/2 minus 2 over 3 u to the 3/2 from 1 to 5. And now let's plug that guy in there. So you're going to get pi over 32. So 2/5 5 to the 5/2 power minus 2/3 5 to the 3/2 power. So this is going to be my first part when I plug in the 5 minus, and I'm going to get my second part, which is going to be 2/3 1 to the 5/2 power minus 2/3 1 to the 3/2 power. Okay, and now if you really want to simplify this, you can. So this guy is just going to give me 2/5, and then I have 5 5/5 under the square root. So I'm going to be taking out 2 pairs, so that's going to give me 25 square root of 5. That's going to be this guy. And then I have minus 2/3. I have 3 5s. And under the square root, I can take out 2, so that's going to give me 5 square root of 5. And then I have this leftover minus 2/3. Oh no, wait a minute, this should be a 5. So you got minus 2/5 minus 2/3. Okay, and I can simplify this a little bit more if you want to. I can get 20 over 3 square root of 5 plus 4 over 15. Okay, and that should be kind of the final answer. You can simplify this as many times as you want. Of course, you could have finished it up here. I think you could have been done here, since this would be the final answer. But you can continue to simplify it if you want. So yes, messy integration. These problems are not nice, but they're not hard. They're just really long. So in the next video, I'm going to do another problem.